Okay, hello everybody. I tried to choose a funny and meaningless title for this talk, but the real story is about refactoring tools, and in particular, refactoring divide and conquer functions. So what I'm going to talk about today is the necessary tooling for analyzing source code, well, Erlang in this case. So we can analyze Erlang source code, find interesting functions, and provide ways to refactor these functions into some form, some particular form, using a tool. And the way we do this allows us to preserve the meaning of the program. So if you choose this kind of tooling, then you can be sure that nothing goes wrong during refactoring. Of course, there is some bounded expressiveness behind this, but of course not everything can be done using a tool, but what you can do with the tool would be more safe than doing by hand. So I should now explain what divide and conquer is, but after Kevin's talk in the morning, I should just say that, yeah, it's hylomorphism. Okay. Okay, so you can see this kind of problem-solving structure in many algorithms, like quicksort, merge sort, bucket sort, Minimax search, and Karatsuba multiplication, and so on and so forth. These are all very interesting algorithms, and they share a common property. The main property is that to solve a problem, you have to split up the problem into smaller ones, recursively solve these smaller problems, collect the results of the solutions of the smaller problems, and then compose these solutions into the solution of the original problem. So that's the main idea. And if I try to formalize this in a pseudocode, I would say that solving a problem starts by investigating whether it is a base case or not. If it's a base case, then we can solve it simply. If it's not a base case, then we have to divide it into smaller parts, then recursively solve those smaller parts, apply the same function on all items on this subproblems list, and then we can combine the solutions to result. Of course, the main idea behind functional programming, or one of the main ideas behind functional programming, that common patterns should be abstracted into higher order functions. So if you want to write it properly, then you would define higher order function which expresses this specific recursion scheme. So in this case, I could just define solve as an application of the higher order DC function, which takes 4 functions as an argument and then produces a function, a solve function. And this solve function captures the same behavior as we have seen on the previous slide. So what is my motivation? Of course, parallelism. Everybody is motivated by parallelism nowadays. So Kevin is interested about megacore computers. That's his term. I think he coined this term, megacore computers. And I am sure that programming this kind of megacore computers, you need very nice ways to describe parallelism. High-level patterns would be the best for this purpose. So I was working together with Kevin and others in a project, paraphrase, parallel patterns for adaptive heterogeneous multi-core systems. And in this project, we have developed a tool for refactoring Erlang programs for parallelism. So there are various sorts of standard patterns, and amongst them there is divide and conquer. So let me show you an example in Erlang. For instance, I have a merge sort, which sorts an empty list very easily, sorts a singleton list also very easily. The trouble starts with the non-empty list. For non-empty lists, you split the list into 2 halves, then recurse on the left half and the right half, and then you can merge the sorted list. Yeah, this is a divide and conquer. It doesn't contain the map function, as we have seen on the canonical example. but everybody can see that this is a divide and conquer function. It's not written using a pattern, but of course we can restructure this code into an application of the DC function, the high order pattern. So I could rewrite this function in the following way. Well, I'm using a special library here. ScalingHLP is a library developed in the Paraphrase project, and it contains algorithmic skeletons for Erlang. So inside this library, we have an implementation for divide and conquer. So we can pass the necessary constituent functions to this higher order function, and it will return a function. So we can apply this function on the input list. And as you see, this is how we decide whether we have reached the base case. This is what we do, identity, when we have reached the base case. This is the division, and this is the combine function. There, of course, you can of course find out how to implement this DC. I don't go into details. This is a sequential implementation of the DC functionality. That's actually a map function call. I apply a function to each item in a list sequentially. But you can turn it into a parallel implementation very easily by using a par map or something. Okay, and of course you could add some more knowledge into this pattern by limiting parallelism, for instance, by saying that I allow this and this amount of processes to be launched during the computation, or by using a variant of DC which can switch from parallel computation to sequential at a given condition. So what we are doing now, we provide tooling. And I think we have reached really far in this. We can find, divide, and conquer pattern candidates. This is what I was talking about last year here in Lambda Days. So maybe you remember this talk. I'm not going to address this issue today. And I don't talk about assisting the programmer in making good parallelization decisions. What I will focus today on is refactoring candidates. Refactoring functions which behave like divide and conquer into an application of the higher order function DC. And all these steps are actually implemented in Party. Party stands for Paraphrase Refactoring Tool for Erlang. And wow, it is actually based on our previous refactoring tool called RefactorErl. So if you try to download the tool what I'm talking about now, well, you will have to look around at the RefactorErl site. So RefactorErl is a static source code analyzer and transformer which has been developed in the last 10, 12 years at our university. It can do a lot. I'm going to use only a small part of it in this research. So for instance, this tool has standard refactorings implemented already, renaming definitions and moving definitions around, introducing and eliminating functions or variables, that's quite standard again, generalization of function, reordering the parameters of functions or toppling the parameters of functions, plus many other interesting refactorings, mostly specific to the Erlang language. But now we would like to see what we can do for divide and conquer functions. So once we have found divide and conquer functions, we would like to apply small, meaningful transformations on the code. A smart programmer probably should know what sort of transformations to apply and in what order to reach eventually to an application of the DC pattern. So for instance, we start out with the merge sort implementation we have seen so far, and then by applying certain transformations, we can reach a so-called canonical form. A canonical form is exactly the same structure that I showed you in the beginning of the lecture. So it's if is base, then we solve the base case. If it's not is base, then we divide the problem into smaller ones, recurse, and then combine the solutions of the subproblems. So if we have this canonical form, then the last transformation will change this code into the application of the DC higher order function. So this is how we expect our tools to work. So what is a DC candidate? Yeah, I'm not going to talk about hylomorphisms. I would just say that a function that calls itself recursively in a very tricky way, we require that the function calls itself multiple times on the same execution path. I'm not going to define what an execution path is. You can use your ad hoc definition in your mind. So it's just what you think of course. And there is one more important requirement, that these calls should not depend on the result of each other, so that they can be executed in parallel. So this is how we try to characterize divide and conquer functions. But these sorts of functions can be written in many, many ways. There are many semantically equivalent syntactic forms that can capture the same concept. Or you can even split up your function definition into multiple definitions and have mutual recursion in your code. These, wow, we can take care of all these various syntactic forms and find the interesting functions for you. But now what to do with them, how to refactor them. So let me show you a very simple example. That's a Karatsuba multiplication. It's very easy to see that this is a divide and conquer function. It calls itself 3 times with parameters that do not depend on the result of each other, so it's fine. Or you can have a more sophisticated example of a Minimax search where Minimax max calls Minimax min multiple times. As you can see, this call occurs syntactically only once, but it is in the head of a list comprehension, so it is probably a multiplicity behind it. And Minimax max calls Minimax min, and Minimax min, well, it's quite symmetric, calls Minimax max, again, multiple times in the same head of list comprehension. So mutual recursion, we have to detect this, and we have to show now techniques to restructure these sorts of functions. So we have introduced novel refactorings to our system. Some of them are actually quite generic. Others are really, really divide and conquer specific. So like transforming function clauses to case expressions or vice versa. I think that's a good thing to have. It's not only good for divide and conquer refactorings, but for many other purposes. Then grouping case branches. Oh, that's another story. I think that doesn't make sense anywhere else but refactoring divide and conquer functions. Bindings to list. Introducing list map, merge function definitions. This is how we try to solve mutually recursive functions. Moving in and out expressions to and from case expressions. So there are refactorings which you can probably imagine. I'm not going to present you all of them now because we don't have that much time before lunch. Dinner. We have already dinner. Okay. So no, I don't tell you all the details about this. Maybe I can show you a few very simple examples. Like here we have the original definition of merge sort, and then we have function clauses with pattern matching, and we can turn it into a case expression very easily. So that's one simple transformation. It's a trivial transformation, but all our transformations are quite trivial, quite simple, so you can see that they are probably sound. While we have not proved that they are sound, not yet. We need to find a proper PhD student for that, but yeah, we have really high confidence that they are sound. Another interesting one, we can group case branches. As I said, this is really, really specific to divide and conquer, because this is where I introduce the distinction between the base case and the recursive case. So here I have the red branches and the blue branch. And I want to replace this single case expression with 4 case expressions. 4 case expressions. First, I would like to separate the blue branches from the red branches. So the first one will just have true or false, depending on whether I am in a red branch or a blue branch. And then inside those two cases, I will introduce more cases. So let me show you the result. So I have an expression which computes whether I am in a base case or not. So that's just computing a Boolean value. And then I'm using this Boolean value in the second case expression, where I have the true branch with a case expression with the true branches, with the base case branches. And the second nested case expression covers now the single recursive case. If I have more recursive cases, then of course I have a proper case expression here. This is a kind of strange case expression which can be reduced to an equivalent form by just dropping the case expression. Then we can introduce function or eliminate function and eliminate variables. I'm not going through all the details now. After a while, we can reach the canonical form. And now we can introduce the DC function in the last step. So that's how we proceed with this simple example. It's very easy. I'm not going to talk too much about this Minimax, but the main idea, as I told you, is to collapse the two functions, the mutually recursive function, into one function. And then you can try to do the same tricks as with the direct recursion. Okay. So let me go to the conclusions. I'm in favor of using pattern-based parallelism. And of course, we need tools. We need tools for everything. Of course, for parallelizing programs, we need even better tools than for others. So we need a tool which is able to discover pattern candidates and which is able to help us to refactor the code without losing or changing the meaning of the code. By applying step-by-step refactoring, small meaningful refactorings so that the programmer can keep them in mind, until we reach to a canonical form, and then we can restructure this canonical form into the use of a higher order function. There are many, many open questions here. Of course, we have not proved the correctness of the small steps, but this should be relatively easy because these are small. Of course, we should find out combinators to combine these small steps into larger transformations, compound transformations. That's, again, one interesting research idea where you can use, for instance, AI methods to find out which is the best combination of the steps. And of course, you can always intervene with manual refactorings in the process. So if you can't do it with the tool, well, you can do it with manual refactoring. I think that's a combination of tool-supported refactoring and manual refactoring. Okay, thank you very much. And if you are interested, I can show you on my computer how it works sometimes. So I have an implementation. Not all transformations are implemented yet. Some of them are already implemented, and sometimes they work perfectly. Sometimes they break, of course, because this kind of beta version. But I'm ready to show you if you're interested. Thank you.
Questions?
One question. In what way you measure how the refactoring your tool does improve the code? How do you measure this improvement?
In this particular case, we don't measure how the code is improved. In this case, we provide a recipe for the programmer, a written document that, okay, if you want to introduce a divide and conquer function, then probably you should apply these sorts of transformations in this order or in other order, but it depends always on the programmer. He looks at the code and sees that, yeah, this should be done. So it's not automatized here at all. Here we need a smart programmer who knows what to do. We just want to avoid copy and paste errors and replace all errors. So we want to help the programmer to perform the refactorings. We don't tell him in which order these transformations to apply.
Thanks so much. What do you do with comments in code when you transformating it?
Who writes comments?
No, we don't rewrite comments. We are proud of our layout preserving refactoring techniques. So the infrastructure behind our refactoring engine is really smart. It really takes care of lexical information. And we have nice algorithms on paper on how to preserve layout. But I don't know what happens. Sometimes it really spoils this. It tries to be so smart that in the end it is terrible. So yeah, but the main idea is not to pretty print with a standard pretty printer all the time, because in that way you lose layout information and comments and all interesting stuff. Instead, we try to be smart and preserve the layout of the code as much as possible. It doesn't work perfectly. It works sometimes.
Any more audience questions?
How many users or application use cases you have for your tool? Can you say something about this?
For this particular refactoring, we don't have any users yet. I hope you will be the first one. In general, we have used the tool in multiple domains. We have a strong collaboration with Ericsson Hungary, and they used our code for various purposes, for discovering bugs, for restructuring modules in a big project, like millions of functions reclustered in a module in a system. And some of our ex-students who now work for Ericsson Hungary, in the remaining small number of Erlang-based projects, they do use our tool for information sharing and code investigation, code comprehension.
So I'm going to abuse my position and ask you a question, Tamás. How does your approach compare with Adam's that we saw earlier? What's the difference between them? And why is yours better, do you think?
I'm not sure. My approach is better than Adam's, especially that one of the co-authors of Adam is Kevin. So yeah, they are equally good. we have to go into details to see what the ideas with the anti-unification are and how we can apply. I think we have a different approach because we represent programs as a graph. We call it the semantic program graph, and we try to perform the discovery process on this graph using graph searches. And this is different the term-based anti-unification approach of Adams. But maybe we can find a balance between the two. Maybe we can improve our search using that idea.